This slide I will explain about addressing mode. Addressing mode is the way the processor identifies the location of data that an instruction needs. It tells the CPU where to find the data, whether it's in a register, memory, or given directly in the instruction. For example, in move D0, D1, the data is in registers. In move #5 D0, the data 5 is given directly. This is immediate addressing.
Hello, today I'll be talking about the addressing mode in Motorola 68000 microprocessor. Addressing mode are basically in the different way the CPU can access data either from register, memory or directly from a value written in the instruction. In the M68000, there are 12 addressing mode. Some commands. One are data register direct, where data comes straight from a register like D0. Secondly, address register indirect, which use the address stored in a register, for example A0. Next, post increment and pre-decrement, which automatically adjust the address before or after access memory. After that, with the displacement or index, where the CPU acts on offset or index to find the exact memory location. And lastly, an immediate mode where the value is written directly in the instruction like #5. So in short, addressing mode gives the processor flexibility in how it writes and process data efficiently.
Hi, today I will explain my program that add two numbers using three addressing mode in the M68000 processor. First, move A.L #num1 A0 use immediate addressing because the address is given directly. Next, move.l A0 D0 use indirect addressing. It takes the value from memory. Then add.l #5 D0 also use immediate addressing to add number 5. Finally, move.l D0 result use direct addressing to save the result in memory. So, this program use three addressing mode: immediate, indirect, and direct to do addition.
For question 4, I wrote an M6 key assembly program that performs subtraction of two numbers using three different addressing modes. The first addressing mode I use is absolute addressing. According to the table, this mode uses an actual memory address as a source of destination in my program. The instruction move val1 D0 use absolute addressing because the value is taken directly from the memory label val1 and moved into register D0. The second addressing mode is immediate addressing. Based on the table, this mode uses data that is already known or written directly in the instruction. For example, in move to D1, the number 2 is an immediate value that is directly placed into register D1. The third addressing mode is register direct addressing. This mode uses data that is stored inside a register. In my program, the instruction sub D1 D0 subtract the value register D1 from the value in register D0. After the subtraction, D0 holds the result of 10 minus 2, which is 8. So the final result is D0 equals 8 and D1 equals 2. This shows how different addressing modes are used together in one program to perform arithmetic operation. In this program, the instruction demonstrate both logical and arithmetic operation using different addressing modes. The program starts at memory address 2000. First, an immediate value for AB7 is moved into register D1. and the NOT instruction inverts all bits in D1. Then another immediate value 5E92 is moved into D3. The OR instruction combines D1 and D3 using a logical OR operation. After that, the add instruction adds D2 and D3 and the sub instruction subtract D2 from D3. This shows how the Motorola 6X000 processor performs data manipulation at the register level using both logical and arithmetic instructions.
This slide I will explain logical instruction in M68K assembly language. Each instruction performs a bitwise operation. For example, AND combine bits or set bits if either is 1 and NOT flips the bits. CLR clears data by setting all bits to 0 and TST is used to test a value without changing it. This slide I will explain arithmetic instructions in M68K assembly language. Add to add two numbers, sub to subtract one number from another, mulu or mulse to multiply numbers, divu or diff to divide numbers, net to change a number's sign, for example from positive to negative, add A or sub A to add or subtract address value, add A or sub Q to add or subtract a small quick value. These instructions help the computer do math in M68K.
Okay, for this question, we need to convert the expression into the assembly language. First, I change all the number into decimal. The binary number is 10111. 111 base 2 becomes 191 base 10 and DADA base 16 is 56,026. Then the octal number 1234 base 8 become 668 base 10. Next, I multiply 191 with 56,026 and add 668. The total in decimal is 10701,634. When convert to hexadecimal, the answer is A34B421 base 6. So this is the value we will use in the assembly instruction. Now I will convert to hexadecimal number DADA base 16 into decimal. Each letter represent a value. D is 30 and A is 10. So I multiply each by 16 to the power of its position. That's mean 30 times 16 power 3 equal 53 to 248. 10 times 16 power 2 equal 2056 and 30 times 16 power 1 equal 208 and 10 times 16 power 0 equal 10. Then I add all the value together. 53 248 plus 2016 plus 208 plus 10 equal 56,026. So DADA base 16 equal 56,026 in decimal. This program multiplies two values using the mulu.w instruction. After multiplying 0x5f and 0x dada, the result in D0 is 0051 3862. Then we add 0x1 is C and the final result becomes 0051 3A3E. It shows how the M68000 perform arithmetic operations.